It is 2.3 time. We got a revolution going on. Volumes of revolution. All right, never mind. I tried to make this catchy and exciting, but we're just talking about in this section volumes, just like the last section with the disk method. They sometimes call that the washer method. It's basically the same method. Last section we had a method for calculating volumes. This section we have a different method for calculating volumes. Sometimes one will be better, sometimes the other will be better. Take a look at this motivating example. Let's say that I had two functions and I only had these functions in terms of y. And I wanted to revolve this region, this yellow region, if I wanted to revolve this about the x-axis, well, what I had to do, well, we'd have to get everything in terms of x. For the disk method in 2.2, revolve around the x-axis, we basically just integrate over x. Revolve around the y-axis, we integrate over y. But that's going to be a pain here. We're going to have to get this in terms of x. We're going to have to get this in terms of x. We'll have to split up the integral into two integrals because they have different ways that we set it up. And it's going to be a pain. But what if I could tell you there was a method that we could just immediately do this with one integral? You might be pretty interested or you might not, but that's fine. That's what we're going for here. Just a way to make certain volumes easier to calculate. Another method that's kind of cool. So to visualize this, we're going to use the textbook because I don't want to try to draw three-dimensionally. So let's think about this situation where we have a function defined by x. And we're looking at the area under this function as our region R. But we're not, if we rotated about the x-axis, that would just be the same as the disk method. We already know how to do that. But what if we want to rotate this about the y-axis? So if we rotate it about the y-axis, this is the volume. This is the surface, the volume of revolution. Goodness. Anyway, this is the volume that results from revolving this about the y-axis. And we can actually set this up and dividing it into different kinds of pieces than we did before. So now let's imagine getting these little slices, just these little Riemann sums. Think of those rectangles. And if we divide that up into a bunch of those rectangles, this is what our volume, our solid of revolution, that's the word I used. This is what our solid of revolution looks like if we divide it into little pieces. Each piece looks like a cylindrical shell. All right. So again, what are we doing? We're revolving it about the y-axis, but we don't want to put everything in terms of y. So we're just cutting it. Think of horizontal cross sections, if you will. And if we do a bunch of horizontal cross sections, we get this resulting figure. Now, each one of these tiny little chunks is one of these. So if we could find the volume of one of these guys and add up all of the volumes, making them thinner and thinner and thinner, that's another way of getting volume. And again, adding up an infinite number of infinitely tiny things in this manner, that's an integral. And the book has the real in-depth, precise definition for why this becomes an integral with a Riemann sum. But again, I think at this point, we can do a kind of hand-wavy explanation in these videos to show where it's coming from. So what is this volume? We're basically using the same method as last time, not the disk method, but finding volumes with cross sections. We took a bunch of cross sections. We're going to look at the volume of an infinitely tiny one, and then we'll add them all up. So let's look at that volume. I'm going to copy that down. Okay, so what it is basically it's a cylinder, but it's not a full cylinder anymore, right? It's a cylinder and it's only a really tiny shell. It's mostly hollow, right? It's mostly hollow in this. We're curious about its little volume. Well, the height of this cylinder, the height is the function value. Now notice the height's going to be a little different at the inner and the outer, but we can approximate this. Say it's a continuous function. If it's a continuous function, then these should be pretty similar as we get really thin. So the height of this, the height is just f of x. Okay. The width of this is some really tiny thing. Let's call it delta x. We'll eventually call it dx. Well, then what's this volume? Think about cutting this on one side, not all the way through, but just cutting it like right here and unfolding it. If we unfold it, we're going to get a rectangle. The height is still f of x. Think of it, this is like three-dimensional rectangle, right? A rectangular prism like this, where you know, the thickness is that dx still. What's the bottom of this? Well, the bottom of this is the circumference, right? What's the circumference of a circle? We're revolving it around the y-axis, so it is a circle. Circumference of a circle is pi times the diameter. Okay. So what's the diameter? Or 2 pi r might be easier as well. The 2 pi r or pi times d. What's the diameter? What's the diameter or the radius of this shell? We know the height is the function value at x, but notice that the radius is just x, right? At any point, this radius, again, the radius is going to be a little bit smaller on the inside than it is on the outside, but we're thinking about as these get really, really thin, that gets really close together. The radius is just the x value. The radius is the x value. So 2 pi r is the circumference. That's 2 pi x. So the volume of just one of these little guys, let's call it v sub I, right? The volume of just one of these little pieces, is just going to be, well, it's a rectangular prism, so just multiply all these things together. 2 pi, let's be consistent with our ordering. Call this 2 pi x. 2 pi x times f of x times delta x. And we need to add up all of these. And again, if I'm being really precise, we should add some i's here for the volume of the ith piece. Now we just add up all those volumes. Sum from 1 to n as n goes to infinity. That's a Riemann sum. That's an integral. This volume is going to be the integral from a to b of 2 pi times x f of x dx. And that's the shell method here. Okay? So again, understanding where it comes from is very useful. We'll introduce it more formally at the end of this video. You don't technically have to know where it comes from, but it's going to make things a lot easier to understand and remember if you do. Let's give a visualization of this. Another visualization of this. I think the book has something else. Again, you can see here the real precise derivation. Here it's showing you if you cut and unfold it. That's essentially what we said right here. Let's look at some GIFs. Okay, so we're looking at what the area under this parabola getting rotated about the y-axis. This is our solid that we're looking at. Another way of thinking about this is one of my favorites, is look at this curve. We're rotating this curve around, and we're doing all these cross sections. So each one of these colors is a different one of those v sub i's that we did. Okay, and each one of those is going to have that shell, and we can just add up all those shells to get it. It's showing it by half at the start just to give a visualization, but now it's really showing that as these get really, really tiny, really thin, it will approximate that whole surface. And here's another way. Each one of these frames, frame, I mean like frame per second, that kind of frame of a GIF. Each one of these frames shows one of those small little cross sections that we're talking about. And we're just adding up all of these guys, all of these volumes to get, again, the region of this parabola, the volume of this parabola, area under it, rotated about the y-axis. So some different visualizations over here. Okay, so let's introduce the method more formally, and then we'll do some examples in the next video. So this is the rule, a rule for the shell method, specifically the shell method about the y-axis. And we have some requirements, just like before. Let f be continuous and non-negative. Again, continuous is important because all of these assumptions that we're making that, oh yeah, if the delta x is really small, then f is close together. That's only true if it's continuous. If it's not continuous, then small changes in x could have huge changes in y. Okay, so, and then non-negative is just for convenience. We can split things up into negative and positive in other situations. So let's say that R is the region between f of x, the x-axis, f of x, sorry, and the x-axis from A to B. Then the volume formed by rotating R about the y-axis is V equals 2 pi R integral A to B, just what we wrote on the other one, x f of x dx. All right, so in the disk method, we had basically pi R squared. Here it's 2 pi x f of x. This one's a little harder to remember, if I'm being honest. Also, this is formally the definition for the y-axis. I'm hoping that you have a suspicion about what this looks like if we instead want to rotate it about the x-axis. We'll do that in the third video, but I'm hoping that you have some sort of guess or suspicion about how this would change if we rotated it around a different axis. And that's all this video is, introduction. Give some conceptual understanding of what's happening here, where this method comes from, just adding up a bunch of shells. And you can use this formula to find some volumes, and we're going to do that in the next video. Good luck.